Morning. Well, we're ready to start the next chapter here, which is actually chapter 10, I think, in your book. Um, and it is complex vector spaces. We have a great application in this chapter, as I always try to do, which is the Fourier transform. And so I want to today just take you through the notes that I typed up, and I've also shared these notes with you on Google Classroom where this video is. And then I think today, this afternoon, later in the afternoon, once we're sure that everyone's had time to watch the video here, I'll text out a code for a meeting for a Google Hangout if you have any questions about my notes with this today. So make sure that you have joined our Remind group. So you want to text Forsyth LA at Forsyth LA for linear algebra to 81010. Those directions are in an email here. So what I want to do is just take some time here to take a look at these notes and kind of guide you through them here. So let me shrink myself up here and I can be on the side. I don't know if you need to look at me while I'm looking at these notes, but I might as well just leave myself there. And so I have them in bullet point form, and you can see I'll be using my cursor arrow here to talk you through this. We'll see how much time we have. We really don't want to spend more than about 15 minutes per day working through stuff here together. That's a directive from the district. So we'll go through some of this quicker because this is supposed to be mostly a review. So we're reviewing complex numbers here because we're going to be using them in looking at what happens when you have matrices filled with them rather than just real numbers here. So again, we all know what a complex number is here at the beginning of the line, and I'm just taking us through these first couple of bullet points here, are just reminding you of how to multiply them out and add them together. Obviously, that's important for us with dot products, scaling and adding. Division is, of course, just multiplying by a complex conjugate, which is defined here. If z is our complex number and our complex number is a plus bi, z bar is the complex conjugate, that's a minus bi. So really, to divide complex numbers, we multiply them by their complex conjugate. And the modulus of a complex number really is its distance from zero. So kind of like an absolute value with real numbers. And so the way that we envision this is actually by plotting. I think you've seen this before. Plotting complex numbers on what's called an argand or a complex plane. And so each complex number here, right, our x-axis would be our real component to it, and our y-axis would be in our imaginary component. So you have basically a distance from zero for the real part, a distance from zero from the imaginary part going up here. And so this modulus is basically the hypotenuse of this right triangle that would be formed there. And because we're looking at them like this, it's often easier for us to think of complex numbers in a polar form rather than a rectangular form here. So you can see what we're doing here is at the bottom, I'm just taking you through how you would convert a number, or any number really, into its polar form. So rather than x over and y up, it's r for the radius, I guess, of the modulus, and theta for the angle of rotation inside this right triangle here. And so a plus bi, since a is the real number, is the real part here is on x, it's r cosine theta, and the plus bi, the imaginary component, is on y here. You have r sine theta for that distance here. So I'm showing you here that a plus bi equals r cosine theta plus r sine theta times I is how you would convert that into polar. And so again, to get the modulus, it's just the Pythagorean theorem. The radius is the Pythagorean theorem, and then the angle, you can use arctangent because you want to make sure that you're rotating into the right quadrant, not just a quadrant 1 or a quadrant 2 for solution from your calculator. And that's how you could get the r and the theta for polar form. So mostly a lot of the cool stuff that we do with complex numbers is going to be using them in their polar form. Okay, and so if you go to the next page of this, right, there's a good example here of how to convert. I gave the example here of square root of 3 minus I as a complex number and how to convert it into its polar form. So it's R is just, again, the square root of 3 squared plus 1 squared. I'm sorry, square root of 3 squared plus 1 squared. And then for 2, and then you just get the arctangent of the values, and you get square root of 3 over 3, which gives you a angle of, in quadrant 4, for 11 pi over 6. So then the polar form of that complex number can be given simply by this. So they're equivalent expressions with that. And then what comes out of this? The reason that we want to start to look at this is because it's going to be a lot easier for us to express complex numbers really as exponentials. And so what I've done here then is we have the showing you just multiplying by a polar form, what it would do to take one integer and then start to square it. And so that derives for us, or raise it to power, and that derives for us de Moivre's theorem down here at the bottom. So if I take you through these bullet points here, so we have two separate complex numbers here. We have z sub 1 and z sub 2. If we multiply them together to see what the product comes out to be, it ends up being a sum and product property from precalc. And so it's these two properties here. And what we can do then is just combine them into one. When you work through all of this multiplication up here at the top and use these properties, you get that the product of two complex numbers, this is two distinct complex numbers in this case we're imagining, would just be basically the sum of the moduli times the cosine of the sum of the two angles plus I times the sum of the second two angles. But de Moivre's theorem takes into consideration, what if you're squaring the number? In other words, what if z1, z sub 1 equals z sub 2? Well, from that, you can see inductively what happens. So if z sub 1 and z sub 2 are the same thing, and you're trying basically z squared, it's going to be r squared times cosine 2 theta plus I sine 2 theta, because theta 1 and theta 2 are equal. So it's just 2 theta and 2 theta in each case. If you continue that inductively, you see that you, for z to the third power, raising a complex number to the third power, you're going to get r cubed cosine 3 theta plus I sine 3 theta, which leaves you to de Moivre's theorem here through induction. The nth power is r to the n cosine n theta plus I sine n theta. I noticed that I just noticed now this should be, to make this on the right side of the equal sign equal this on the left side of the equal sign, that there should really be parentheses around the r here too. So if you print this out, put a parenthesis right here and a parenthesis right here in the end, and then it equals, and then it makes sense. Okay? So basically that is looking at raising complex numbers now to powers, but expressing them in their polar form here. I'm watching the time here because, again, the directive from the district has been to give you about 15 minutes or so of work, 15 to 20 minutes for at least this first week here of the day, and I'm already on 10, I believe. So I'm worried. You know how worried I always get worried about running over time. It looks like that's going to happen again here. Because on the next page, what we have here are roots of a complex number. So I'd actually prefer to wait on that, I think, for tomorrow, because what I'll do then is, if you watch this video, I'll give you just a couple of problems to practice with that. So just the things that we've gone through today. So just some basic complex number theory with addition and subtraction of complex numbers, multiplication, division of complex numbers, conversions to polar form, and then the basics of using de Moivre's theorem here to express a complex numbers to a power. So what I want you to do then is make sure that you've read my email about how share work with me, I want you to create a folder. And I was specific about how I wanted you to title it. And I want you to share that with me. And that's where you'll put pictures of all of your work. And I will also be specific of how to title the work, so that you can, I can find it easily and we can get credit for what we're doing there. So I am going to post a couple of problems on this classroom post as well. And you can try them. And the district says that you have 5 days from the time I assign it to turn it in. So really, I won't be checking for about a week to see that those 5 problems are done. But please keep up with it, because I am going to try to stick to the 15 to 20 minute time period that they've asked us to do. And I hope to, I'm not going to load a ton of work on us through this, as long as we're staying with it. So I think that's good for today. And then tomorrow we'll go into further pages in these notes together, and we'll look at some more problems with them tomorrow. So I